Okay, so you guys remember what a graph is, right? It's a graph theory combinatorics kind of graph. So a bunch of vertices and a bunch of edges between the vertices, right? And a graph is set up is Euler or has Euler trails and Euler circuits. You know, by definition, it means that you can find like a way. So let's say that's the graph. You can find you can sequence the edges so that you're basically going you're going around the graph, but you're only visiting each edge exactly once. Yeah, so this could be like 1, 2, 3, 4. Yeah, that's an Euler circuit is if it starts and ends at the same point, and a trail is if it might not start or end at the same point. So Ryan's not paying attention already, and you're the only one I'm actually saying this for. Do you understand? Okay, so that's the definition. The theorem is a graph has an Euler circuit, okay, if and only if, so circuit, if and only if each vertex has even degree, okay? You know what that means, degree? It has an even number of edges coming out of each dot, you know? And the reason for that is basically, well, we're not going to prove it, but
one goes in, one goes out.
yeah, like if it goes in, it has to come out, right? Or it gets stuck there. So the in corresponds to the out, so they're always paired up to be even. And the only difference is if it's a trail, there might be two odd degree vertices, okay? And the rest even degree. Okay, and can you guess what the odd ones are for? Right? Yeah, they're the starting and end points, okay? Because if you start, it has to be odd to get out of it, right? And if it ends, it's odd to get in. Yeah? Okay. So that's the Euler. And what are we going to use it for? Well, believe it or not, this 2020 ASC question 2 obviously doesn't have to be done this way, but it's a very nice example of it. Okay, so the question says you got an m by n grid, yeah? And you want to, like, for which m and n is it possible to label all the cells from 1 to all the way up to mn, right? Such that consecutive numbers, so like I and I plus 1, they have to be in the same row or column, yeah? And but if this is in the same row or column, then like the next one has to be so if this is same row, then the next one has to be same column, yeah? Or another way of saying it is you can't have 3 consecutive in same row or column, yeah? So it can't not 3 consecutive in the same row or column. Okay. And the question is, for which m and n is it possible to do this numbering of all the cells? Okay. So for example, if you had like a 2 by 3, you could do 1, 2, 3, 4, 5, 6, yeah? So these are in the same column, same row, same column, same row, same column. It alternates, yeah? Okay. Okay, so the cool thing about this problem is not kind of just solving it normally, which you can do quite easily. It's relating it to this Euler circuit, okay? So the claim is that Euler trails and circuits correspond exactly to the numberings of this grid. So what do I mean by that? So you need a graph first, yeah? graph. So the vertices of this graph, okay, I kind of want your full attention, yeah? But you're not quite there yet for half attention, okay? So vertices are the rows or columns. Yeah, so I don't like this idea of just like waiting for the answer. See, like you don't know what the vertices are and you don't know what the edges are, okay? But you're waiting for me to tell you with half your attention somewhere else. Okay? So the vertices are the rows and columns of the grid. Yeah? Okay. The edges are the cells. Okay? And so if a cell is in row I and column J, then it's an edge between row I and column J. Yeah? That makes sense? So the cell, like, so if you have like this grid here, yeah, then you'd have row 1, row 2, C1, C2, C3, yeah? And then this cell, that would act as an edge between row 1 and C1. Okay. This cell would act as an edge between row 1 and C2. Yeah? Okay. And so on. Okay, so the kind of graph you get, so you have like R1, R2, C1, C2, C3, yeah? The kind of graph you get is like this. Yeah. Yeah. So we actually get what's called a complete bipartite graph. Okay? So basically the rows never connect to the rows, and the columns never connect to the columns, but they connect to every single one of the other. So the row connects to every column. Yeah? Okay. So this is called a complete. Complete just means it has as many edges as it can have. Bipartite means it doesn't connect to things, like rows don't connect to rows. Okay? And with a complete bipartite graph, it's kind of obvious what the degree of each vertex is. Yeah? So the degree of every like row vertex is equal to the number of columns. Yeah? So the number of columns is n, yeah? And the degree of each column vertex is the number of rows, yeah? This is for all I, for all j. Okay, does that make sense? So here there's 3 columns, so there's 3 vertices, there's 3 edges coming out of each of these, yeah? So these have degree 3, and these have degree 2, yeah? Okay. Now, okay. So what I want to show is that the Euler theorem precisely solves this problem. So there's no even extras. So for every Euler trail or circuit, or just every Euler trail, and suppose circuits are examples of trails, every single one of them, you can do a numbering from 1 to n. Okay? Every one numbering from 1 to mn, you get an Euler trail. Okay? So how does this work? So it's a bijection, okay? So bijection, you know, you can do like injective, surjective, or the most natural way is to do like one way and then inverse, okay? So you start with an Euler trail, yeah? Does that make sense? Start with an Euler trail. What's an Euler trail? Well, it has to use, so like with log, it starts on a row, yeah? It doesn't matter if it starts on column or row. So it could be like a row I1, yeah? And then it goes to column I2, J1, and then it goes row I2, column J2. So basically, it just keeps alternating until it gets to the end, whatever is the end. It's either R or J, right? Or a column or a row, yeah? But the point is, because it's Euler, it has to use all the edges, yeah? So there should be mn edges, yeah? Okay. So then what do? You just take the edges in this Euler trail and you number them 1 to mn, okay? Because each edge is a cell, right? So here, so the edge here is the cell I1, J1, right? Yeah. So you just put a 1 there, yeah? And then here it's J1, I2, so the cell is I2, J1, right? Yeah. And then you put a 2 there, okay? And notice that the 1 and 2 are in the same column, yeah? They have the same J1. Yeah, so it satisfies the condition, yeah? And the next one, so the next one is I2, J2, and so that has the same row but not the same column, yeah? So it satisfies the condition. Yeah, so if it has the same row and the same column, then you're reusing the edge, right? If it has the same row twice, it means you're not alternating, it's not bipartite, right? And so it satisfies the conditions, yeah? So therefore, and because there's mn edges, you get all the numbers from 1 to mn. So from an Euler trail, you can get a numbering. Okay? Alright, suppose you get a numbering. Suppose you got a numbering. Okay, so you number the cells, like for example, I1, J1. That's like where 1 goes, yeah? And then say 2, so we'll log that 2 goes on the same row as 1. It could go in the same column as well, right? If it goes in the same row as 1, then 2 will be in I1, like say J2, yeah? Okay, and then 3 has to be the same column, so it's like J2, I2, yeah? And then 4 will be in the same row, but a different column, right? Yeah? So that's like, it has to satisfy the rules, yeah? And if that's how the numbering is, you can define an Euler circuit, Euler trail, okay, by using these as the edges, okay? So this, you take Ri1 goes to Cj1, right? And this one you take J1, sorry, I think I have it the other way around. Sorry, yeah, Cj1 to Ri1, yeah? And then Ri1 to Cj2, yeah? And then the next one is Cj2 to Ri2, yeah? And then here we have Ri2 to Cj3. Okay, so wherever the numbers go, you just keep following it in the trail. Yeah? And because the numbers go all the way up to mn, then the trail has to get all the edges, right? And because you can't have 3 consecutive in the same row column, then you can't repeat edges. So that's exactly an Euler trail, right? So to prove...
How do you know, like, Euler trail cover all the numbers?
All the what?
Numbers.
Yeah, so that's one. So if every numbering, so this could be any numbering, right? This is just an arbitrary numbering, yeah?
Also,
Yeah, so for any numbering, you get an Euler trail, right?
but the numbers might not be in order. You can get an Euler trail, but you don't know if it's in order.
In order of the numbers? What do you mean?
Don't you like number each edge in order?
So the numbering is like a numbering of the cells, right? So it's like 1, 2, 3, 4, yeah? And then what's the issue?
numbers have to. Oh, okay.
Oh, you're answering your own
Okay.
question.
Because I thought numbers could be like 1, 2, 3, 4, like nothing.
Oh. Yeah, the numbers have to satisfy the criteria. So you kind of find each criteria basically corresponds to one of the Euler definition. Okay. So that shows like I guess that kind of shows. So one direction shows there's sort of more numberings. So the first direction showed there was more numberings than trails. And this one shows there's more trails than numberings. So but you're not completely done. The correspondence they should be related to each other. Yeah. So like they should undo each other. Does that make sense? So like if you had a Euler trail, right? Then you did a numbering, yeah, and then you use this to get back a trail, yeah. You should get the same trail that you started with. Does that make sense? And it's kind of obvious that you do, right? Because yeah, the way you numbered it was exactly you numbered 1 for that edge, right? 2, 3, and so the trail literally you get back the same numbers, right? And if you start with a numbering, you get this trail, and then to get back the numbering, well, you're literally just putting the numbers in the edges again. So you literally, so not only is it like these are functions, they're inverses of each other, yeah. So that's like literally what a bijection is, yeah. Does that make sense? So basically, the numberings are exactly the same as Euler trails. So you just need to know what M and M give you Euler trails, right? Okay. So remember, we know the degrees. The degrees of all the vertices are M and N, right? Yeah. So if they're both even, yeah, then we know by the theorem there's an Euler circuit, and you're good. That there's a numbering, yeah. Okay. But what if one of them's odd, yeah? Okay. Well, we'll log that N is odd, yeah. If N is odd, right? Let's say, then the theorem says that there can only be 2 odd ones for the endpoints, right? So, well, if n is odd, there can only be two things with degree n. That means m has to equal 2, right? Makes sense? Like, so you have a bunch of rows, right? You have a bunch of columns, yeah? So like the degree, these are all degree 4, and these are all degree 3, right? Yeah. But you want if that's odd, you want this to be degree 2, right? Yeah. Sorry. If that's odd degree, you only want there to be 2 of them with odd degree, right? Okay. So if there's only 2 of them with odd degree, then the number of rows or the number of columns is equal to 2. Yeah. Not getting it.
Wait, why does m have to equal 2?
So I'm just saying, like, if the degree is odd, right? Yeah. There can only be 2 of them. Yeah. And m is how many there are.
Yeah.
Okay. Because the degree of the other one is how many there are, right? Because that's how many you need to connect. Like it needs to connect to 4 of them, yeah? So the degree is how many there are here. And so the degree is m, yeah? So then m has to be 2. Does that make sense? So n is allowed to be odd, but m has to be the 2 then, yeah? And so then the solution is either m and n are both even, or one of them is odd and the other one's 2. Does that make sense? Hmm? Yeah, so once you make it equivalent, then the theorem is just saying like the vertices all have to have even degree except for two of them. Yeah? But the problem is all the vertices have basically the same degree, right? And so if
Oh,
yeah, all like these vertices all have odd degree, right? So there can only be two of them. That makes sense? Yeah. Okay. Yeah, so that's kind of a neat way. Like obviously, like I mean, Lucas came up with it in the exam. Okay. So it was a bit overkill for the question, but I think it's a very nice application of the theorem, right? Yeah. Any questions?